This conference will now be recorded.
Okay, so hey, thanks Anu. Thanks for confirming it again. Great. Okay, so let me first define the agenda for today's class. So for today, we're going to be discussing, the boosting algorithm. I think in the last class we have completed, our bagging and random forest algorithm, and we saw its use case in Python, right? So how do we write the code for implementing a bagging algorithm, or how do you write a code for implementing a random forest algorithm? So now what we're going to do today is we're going to jump into boosting. Okay. So boosting is once again more like an ensemble of models, right? So you're trying to basically, create a lot of decision trees which are going to improvise each other. So that's a kind of a concept we're going to discuss. We'll understand what's the max at the backend, and then we'll also quickly see a small case. The same thing, the same extension of the digit recognizer we had in the last class. We'll try to implement it here in boosting. And then what we're going to do is, guys, we're going to jump into a very interesting topic, which is neural networks. Okay. So I think we have like small topics like PCA and all, which can be, waiting for, another day. It's completely okay. It can wait. But probably what we'll do is we'll jump into neural networks, where the neural networks has once again a lot of similarity to the boosting algorithm. Okay. In terms of its way it's working, it is a little similar to many of the base models that we have discussed. So I think it should be very easy for you all to follow. I think it's a pretty hot topic, right? And most of us would be very eager in understanding how neural networks works. So I think that's going to be the agenda for today's class here. Okay. Great. So before I get started, if there's any questions regarding the previous classes, any doubts or clarifications you guys want to ask me, feel free to drop your question now. Then I'll probably start in a minute or so if there's no questions. Okay. Okay. So let's get started. So what we're going to do today is, guys, as I told you all, we'll jump into the boosting algorithm. Okay. So first, let's even go back to random forest bagging. We'll ask this question on why did we have to discuss those two. So we're basically saying, hey, I am capable of creating something called as decision tree, right? What is a decision tree actually doing? It is just taking up our data. It is trying to segment them into small segments of data based on certain rules. So the work of a decision tree is basically to come up with all those rules that we see, right? And what he's merely doing is on the small subset that he's creating, right? He's just creating a very simple probability model, or he's creating a very simple mean model when it comes to regression. So when it's a classification, he's applying probabilities. When it's a regression, he's applying a mean model, correct? So the decision tree is actually too simple, guys. All it's doing is it's just segmenting and then it's applying this mean or a probability, right? So the question is, can we make it more complex? Because I see that, it may not have much of a predictive power. It's just plain probability, plain mean. Do you think we can make it much more better? The answer is yes. That's when we started creating ensemble of models, which are random forest and bagging, right? So what did we say? We said, hey, a single decision tree alone may not have a very good predictive power. It might be lagging a lot because all he's doing is he's just segmenting the data and he's applying plain probability equations or plain average here at the bottom when it comes to a classification or a regression. We are thinking that probably its predictive power is not going to be so good. So do you think we have certain methodologies which can improvise it? The answer is yes. Why don't we start ensembling them? So we're basically saying, hey, let's go back and create an ensemble, shall we? So if I'm going to create an ensemble, what are the options we have? We have something called as bagging, which we have already discussed. Then we have something called as random forest also. In bagging, what is he doing? He's saying, go back and take different bags of samples using something called bootstrapping and start creating different decision trees, right? So he says, go back and take up different bags of samples. So what is actually changing here? the data alone is actually changing. So each and every decision tree is going to meet different data. Why? Because you're basically doing random sampling with replacement. So what do we mean by random sampling with replacement? If there's any particular data point, right, the data point might appear many times in one bag. It may not appear in another bag. It might occur once or twice in another bag. So the data is going to be pretty random. You know, the randomness is basically happening in the data. Now you go back and create decision trees, and now you say, hey, these are the different decision trees. I think most of them are unique with each other. That's good. So you're basically making use of different data and you're creating a lot of randomness. Then we average it out, it's good. But random forest is saying, hey, along with bagging, right, whatever he is doing, I'm also going to do random subspace selection. So what is he saying? He is saying, hey, I'm not just going to keep changing the data also, okay? I'm also going to keep changing the variables on which they are actually working. So I'm not going to use up all the variables like what, you know, a plain decision tree or a bagging might do. I'm going to randomly sample variables, and only those variables will be used in the creation of these decision tree models. So in my case here, random forest is saying, hey, I've introduced a second source of randomness where the data as well as the variables are changing. Now you can see that the decision trees are more and more non-unique to each other. There's a lot of dissimilarity between them. Now you go back and get the predictive powers of all the people. So different characteristics of people, if they give you the same answer, you're much more comfortable, isn't it? So one guy is having his own predictive power, another guy is having his own predictive power. When everybody is agreeing on the same answer, you have much more better confidence on the results, isn't it? So now we are saying, hey, random forest is creating different decision trees based on a second source of randomness also, which is variables, random subspace selection. Now comes somebody called as boosting, guys. Okay. So what is boosting actually telling us? Very simple. If you go to random forest, right, we discussed 2 points if you all remember. The first point is that the correlation between the decision trees should get lesser and lesser. Only then the whole random forest predictive power will go higher and higher. Number 2 was, we said the strength of the individual decision trees that we are creating should go higher and higher here. Only then the random forest predictive power will also be better. So what are the 2 points on which we discussed? We said, hey, only if the correlation between the trees are lesser, which means each and every person are using different set of variables. I see a lot of dissimilarity between them. So the correlation between the trees, if it's getting lesser and lesser, I create a better predictive model. If the strength of the decision trees are getting better and better, once again, I'm creating a better predictive model. And we understood that correlation and strength are basically a trade-off, isn't it? So when you use more number of variables, strength goes up. When you use less number of variables, correlation comes down. So it's a trade-off. Whether should I increase the variables or should I decrease the variables? Am I getting lesser correlation or am I getting more strength? It's more like a trade-off that you need to decide. So this is a very important point, right? Where we said the strength of the individual decision trees are going to decide your total model's predictive power. Now boosting is saying, hey, don't worry, I'll try to help you solve this problem also. So what is he saying? He's saying, I'll help you create decision trees which are much more powerful. They are very strong. So boosting is saying, hey, I can help you, randomly sample data. I can also help you randomly sample variables. And I also have a method by which, in spite of doing both the things, I can give you more strength here. The strength of the individual trees can also be improvised by one of the methodology that boosting is actually going to follow. So what a boosting is actually telling us is, guys, compared to bagging, random forest and all, where all the decision trees are completely independent. They're all completely independent, isn't it? One person is not looking up into what is happening in another guy. All the decision trees in bagging or all the decision trees in random forest, they are all completely independent, aren't they? But look at boosting, it's not so. Every decision tree that you create is actually a improvisation over the previous one here. So what's happening in boosting? In boosting, the algorithm or the method has been designed in such a fashion that, guys, compared to bagging and random forests where the decision trees have been independent, where the creation of one person is not affected by another guy. They're completely independent. So first decision tree says, hey, I don't worry about what's happening in second or third. Second or third is saying, hey, I don't worry about what's happening before and after. We are completely independent. But in case of a boosting, they are all dependent upon each other. So we're saying, hey, if this is your D1, right? Your D2 is nothing but an improvisation over your D1. If this is D3, D3 is an improvisation over D2. D4 is an improvisation over D3. D5 is an improvisation over D4. So practically, I can't keep claiming that, the strengths will be better off, guys, but theoretically, that's what we are thinking, okay? But practically, it's not so. 90% cases, you will see it. Every decision tree you create will be an improvisation over the other. But as I told you, practically in 10% of the cases, it may not be so, okay? So what's actually happening is it's actually improvising the predictive capability at each and every iteration or at each and every step here. So decision tree 1 is saying, hey, I have this much of error. Decision tree 2 says, okay, you give me this as an input along with the previous model. I will create a new model D2 which will give you much more lesser error. This will be given as an input to D3. He will create a model with much more lesser error. He will be given as an input to D4. He will create a model with lesser error. This guy will come up with another model with lesser error. So you need to give in the information of what is the error faced by the model so that the next stage of model will go back and rectify that particular error for us. So what is he actually going to do? He's going to go back and rectify that particular error made by the previous case here. This is exactly what is the standoff feature and the differentiator between boosting versus the other class of models. So let's please understand, guys, it starts off with decision trees, then over to bagging, then over to random forest, then over to boosting. And every model here, we are trying to solve one problem. Decision tree as a single model is not good. Okay, let's create many. But creating many that are more or less like similar to each other. Can I, bring down the similarity between them? Sure, why not? Let's create random forest. But when I do random forest, I see that the decision trees are not so strong. Can I solve it? Of course, yes, you can do something called boosting. Now, if you guys ask me, how do you think is neural network kind of very similar to this one? I'll tell you neural network is the same case. Basically, we have a concept of something called perceptron or layer, okay? Everybody is basically connected to each other. In a boosting, it is always a one-way method, right? So you're basically saying D2 will be an improvisation over D1. D3 will be improvisation over D2. It's more like a, one direction. But in neural network, it is like both the directions. It's actually both the directions. So this guy says, hey, I am facing this much of error. He will say this much error. This guy says this much error. This is the total error. Then from the back, you go back and rectify everybody. So this guy retrains himself. He retrains himself. He will retrain himself and goes on till the first. So the difference between boosting versus neural network is in boosting. Okay. Guys, is my voice breaking? I see that there's one message where somebody is saying the voice is breaking. Is it for everybody? Okay, for others, right? Okay. Okay, cool. So Manohar, just check your net connection if it's okay, right? I think it's probably good with others. Okay, so going back here, guys. So as I told you all, in boosting, every model that you're creating next is an improvement over the previous one. So you don't go back and say, hey, the old ones I've created is bad, isn't it? Shall I go back and change? No, you don't do that in boosting. So you just say, okay, now you have committed this error, it's okay. Next time, make sure you don't do it. So, okay, he has committed some error. Next time, make sure that he doesn't do it. You don't go back and say, hey, I think this is the error you made. Why don't you retrain yourself? That is not happening in boosting, while that is happening here in neural networks. So please understand the difference, guys. In boosting, every model is an improvisation over the previous one. It's more like a forward-looking direction. Okay, it's more in a forward fashion, futuristic fashion. It's not having any backward fashion. Whereas in a neural network, you say, hey, I think because of you, he is having some error. Because of you, he is facing error. Everybody is facing some error. Why don't we go back and rectify everybody starting from the first? So this is what we call as feed forward propagate. This is what we call as back propagate. There are two stages. In a feed forward propagate, we go back and check who is having how much of error. In a backward propagate, we go back and say, why don't we all rectify ourselves so that altogether we'll give a good result to the user here. So this is the difference, guys. Okay, please understand, you may see a lot of similarity between boosting and artificial neural networks too. Okay, but this is the plain difference between them. In boosting, you don't go back and rectify the previous model, but in artificial neural networks, you go back and rectify the previous model. So that is the difference here. Okay. So with this said, now we'll jump into our boosting algorithm here. Talking about boosting, guys, there are different versions of boosting that is available today. Okay, so people, started their usages with something called AdaBoost. Once again, he is like the backbone for every boosting algorithm you will meet. Then you have something like GBM, gradient boosting methods, very similar to AdaBoost. So we will be discussing this guy, but we will be implementing this guy. Number 3 is you have people like something called XGBoost and all, today very popular. Then you will have something called as Light GBM. Light GBM is basically the same GBM, but it was done by Microsoft. This algorithm was basically developed by Microsoft. Then you have number 5. There is something called CatBoost, which is also people using today. So this is basically a company called Yandex. They had developed it and they made it as open source. So there are a lot of boosting algorithms available, guys. AdaBoost is one of the forefathers, then followed by GBM, then you have XGBoost, you have Light GBM, you have CatBoost. But this is more like the, forefathers, as I told you. When you compare with any algorithm, you will find it is 95% similar. There'll only be small differences. Here and there, they will tweak it. But otherwise, 95% of the cases, it is the same thing. Same concept, no change to the concepts at all. So what we will do is, guys, we'll discuss the boosting algorithm generally. Here on the left hand side, you see it for a classification purpose. Here on the right hand side, you see it for a regression purpose. Okay. So the diagrams depicted here on the left hand side and the right hand side are basically classification and regression respectively. So what happens is, guys, let's look at the first box that you see here. Okay. So what has happened is he has basically sampled a particular data. Let us say the entire data set was used. All 100% of the data set was used. Okay. What is going to happen is he's saying this is the data set. I will create a decision tree here. So what is he doing? He is creating a decision tree with the split something like this. And then he says, hey boss, people on the left hand side are all positives. People on the right hand side are all negatives. So what is he doing? He's basically creating a small split here, and he goes back to say that, hey, in this split, if people are having values less than this value, it is called positive. If people are having values greater than this particular threshold, we call it as negative. That's a classification he's giving. So from this classification, what's actually happening? All these people have got correctly predicted. These people have got correctly predicted. This guy also has got correctly predicted. But who has got misclassified is basically these three guys. These three members have got misclassified. So what you can see is, guys, your decision tree one is saying, hey, I've committed some errors here, okay? These are the three people who have got misclassified. So they will become my error. So in iteration number one of your boosting, you created one model. Now what you're saying is, hey, in iteration number two, let me pass on the information that these three people have got misclassified. So he will pass on this particular info. What is this iteration number two doing? He is saying, don't worry, I will do something. I will basically give higher weightage to this particular data point and make sure that they don't get misclassified. So what is actually this guy doing? He's saying, hey, don't worry, I'll just go back and give a higher weightage to these data points, okay? And I'll make sure that these people are not getting misclassified. Which means what? So for any other data point, if they're getting misclassified, say for an example, the error that you will pay is 10%. I'm just assuming. For other data points and all, if I make a misclassification, the error might have increased by 10%. But if these three people are getting misclassified, right, because they have a higher weightage, I will say the error is probably right now 50%. I'll make it like 5 times. So he's saying what? Other regular people, if they're getting misclassified, the error would have been just 10%. But don't worry, in my stage, I will make sure that these people are given higher weightage. So by any chance, if I make an error, it may get bigger like 50%. So don't worry, I'm going to make sure that this doesn't occur. I'll somehow make sure that these three people are getting classified correctly right now. So the decision tree 2 said, okay, these are the three people you misclassified, right? Don't worry, I will give a higher weightage to them. Why? Because people given higher weightage will blow the error up. So I'm going to make sure that they don't blow the error up, which means I need to basically correctly classify them. So that is exactly what the decision tree 2 is also doing. So decision tree 1 was able to basically divide them like this. Now decision tree 2 is saying, since these three people were given a higher, weightage, you can see that he creates a split here, and now he says, hey, people on the left hand side are positives and people on the right hand side are negatives. Now what's happening? Even though these three people have got correctly classified, these three people have got misclassified, who in the next stage will get a higher weightage right now? And decision tree 3 will make sure that these three people are not getting misclassified right now, and he'll create a split in that particular fashion. So this is exactly how it will keep happening in an iterative procedure, guys. So this guy is looking up to this guy and he's asking, hey, what is the error you have made? This guy is looking into this guy and he's asking, hey, what is the errors you have made? Another person will ask, what is the error that you have made? So at every iteration, you're trying to make sure that any data point which is getting misclassified in the previous stage is ultimately getting corrected in the next stage here. So what are we actually doing here? We are creating 3 decision tree models by the end of the day. So this is decision tree 1, this is decision tree 2, this is decision tree 3. Ideally, 2 should be an improvement over 3, but it need not. So because he's trying to solve D1, there may be equal number of people who are getting misclassified here also. So it need not be there. Practically, it's not going to happen, but theoretically, it should happen. Every person should be an improvement over the previous one. Now, finally, what happens when there is any given unknown data point? Okay. So let's say you have an unknown data point. This unknown data point will be passed to all the 3 people. And now the predictions coming from all the 3 people will be combined together, P1, P2, and P3. So you have an unknown data point, right? This unknown data point will be sent over to all the 3 models that you see. All the 3 people will give you a prediction. Using that, you basically ensemble to come up with the final probability here. Once again, there's a small point here to discuss. I'll come back in a minute. Okay. So there's a small twist. It's not a plain average, it's a weighted average. So I'm going to come back on this particular point in a minute. So these are the three decision trees. We have an unknown data point in near future. We're just going to pass on to all the models that you see here, and then we'll get the predictions, and we will basically do a weighted average right now. Now coming to the question on why did I mean a weighted average? Very simple. When we know that the decision tree 2 is going to be better over decision tree 1, and decision tree 3 is going to be better over decision tree 2, and it keeps going on, why would you give equal weightage to all the people? You clearly know that the later on the decision trees are getting created, they will have better predictive power, isn't it? Then why would you give equal weightage to all the people? Now we will just go back and say, hey, you have had a little bit of an error, right? So what I will do is, since you have a higher error, I will give you a lesser coefficient like alpha. What are you having? You are also having a little bit higher error. I'll also give you a lesser alpha. But you seem to be having the least error. I'll give you the highest alpha here. So alpha is basically what? Alpha is a model coefficient. It's more like a model weightage, a model coefficient. So you're saying, hey, lesser the error, more is the weightage. More the error, lesser is the weightage. So there are three models. Based on the errors that is occurring from the three models, I'll give coefficients to them. So the more the error, lesser the coefficient, lesser the error, more is the coefficient. Now what you would probably do is you'll say, hey, I will give 20% weightage to P1. I will give 30% weightage to P2 and probably 50% weightage to P3. So he's saying what? Hey, P1 will take up 20% weightage, P2 will take up 30% weightage, P3 might probably take 50% weightage. You're basically deciding it based on the error faced by the individual predictive models here. So this is exactly how a boosting model is once again a little bit different over the conventional modeling techniques we've discussed. So a point to add is they don't just try to improvise the strength of the decision tree at the previous cases. The final outcome that you're getting is also not a plain average, but it's a weighted average that he's going to do. While all of these people were using a plain average. That is once again another superb difference between a bagging random forest versus somebody like boosting. You see it, right? At every stage, they're trying to improvise something, right? Everything, wherever there is a possibility of improvement, they're trying to improve it. Decision tree problem, bagging problem, random forest was a problem. Then boosting came up with all the solving solutions here. So he said, I'll try to improvise the strength of the decision tree in an iterative fashion. Then he said, I'll not combine the predictive power by giving equal weightage. I'll give a weighted average kind of a methodology for combining them. So this is exactly how a boosting algorithm is very, very unique compared to all the other algorithms that we've discussed till now. Okay. So are you all comfortable with this one, guys? The theory behind boosting. I'm going to jump into the max. The max is going to be the same thing. All the story that I told you right now, that is exactly going to be the mathematical equations. Before I jump into it, are you all convinced with the theory? How is boosting different over other models? So they're keeping something called data point weightage. Then there is a model weightage. All these points clear. Why do they keep a data point weightage? Why do they keep a model weightage? Anu, is it okay? Nizam, Manjeet, Manohar, Rakesh, Ravi, Sanjay, Savik. Okay. Okay, perfect. So now let's jump into the mathematics behind it. It is the same story that I told you, converted into max. That's all. Same story, just converted as max. So they're basically saying, hey, let us first take up all the observations and let's give them equal weightage. So he says what? Hey boss, in iteration number 1, right, the very first model that we're going to create, we need all the data points. Sure, why not? I've taken up all the data points. Let's give everybody equal weightage, shall we? So what is he saying? He's saying W of I is equal to 1 by n. So if you have 10 data points, every data point will take 1 by 10 weightage. If there are 100 people, it will be 1 by 100. If there are 1000, it will be 1 by 1000. So Wi is equal to 1 by n, where I runs from 1 till n. Let's give equal weightage to everybody. So going back here, I have right now given equal weightage to all the data points, because still I haven't created any model, still I haven't told anybody has got misclassified and all. So for now, I'm going to give equal weightage across to everybody. Perfect. Now you're saying, let's jump into the modeling step. So this is your modeling step. So in the modeling step, we are basically saying, why don't we use a for loop and we do this iteration many times? Small m is equal to 1 to capital M. What is capital M? The number of models you want to create. So we will go back and say, hey, capital M is equal to 3. I want 3 models, 1, 2, 3. So he's saying, okay, sure, I will take M is equal to 3, which means I'll do 3 iterations of all of this step. Cool. So what are the steps that we're going to do? Very simple. He says in iteration number 1, where M is equal to 1, that is the first model I'm going to create. I will call it as C1 of X. So we are saying, hey, fit the classifier C1 of X on the training data set that we just sampled out using the equal weightage that we just assumed. So we say C1 of X on the training data where everybody has been given equal weightage, because now only you're creating a model, right? So let us give equal weightage for everybody and let's create a classifier. Sure, I've created my classifier Cm of X, which is C1 of X right now. As we told, yes, he has created the decision tree model. Good. What is the next step? He'll give the predictions, left to who is there, right what is there. So step number 1 is he took equal weightage. Then what did he do? He created the model. Now what is he going to do? He's going to give the prediction. After the prediction, you ask what question? Who are the people who have got misclassified? So now go back to the algorithm. You can see here, he is saying, I'm going to give you the prediction and I want to go back and find what is the error faced by this particular decision tree. As a whole, can you please tell me what is the error faced by this particular decision tree? That is, I want the epsilon of 1 is what we are saying. I want the total error faced by the model first. Sure, very simple. So see here guys, what he is saying is yi is nothing but the true value. Please pay attention. From now it could be a little confusing. So yi is nothing but the true value. Okay, so yi is basically what? It is your true value. You are asking a question. Cm of xi. What is xi? It is your input that you're passing. Cm is the model that you've created. This is basically the prediction. You're asking question, is the true value not equal to the predicted value? So what is this equation saying? I want the information, or I want to know what is the error, probably more like that. We are saying, tell me if yi is not equal to the prediction. So what will you say? You'll say 1 or 0. 1 means what? Yes, they are not equal, which means it's a misclassification. 0 means yes, they are equal, which means it's a correct classification. So what will this guy tell us? He will tell us 1 or 0. 1 means yes, it is misclassified. What I predicted and what the true value is different. While if it is 0, it means what I predicted and the true value is equal. What are we doing? We are saying I need this particular input. So what are we doing? We are saying I need this particular input. Now what I will do is, based on the 1 and 0, I'll multiply it with the weight of the data point. So we are saying, hey, the first data point has taken 10% weightage, okay? Second data point is also having 10% weightage. So now you're saying, hey, this data point has got an error, okay? So the error is basically what you're saying, 2 units. But now you're saying here there is no error, it is basically 0. So multiply, you will get what? 20, and here you'll basically get 0. Add it up, total error is 20, isn't it? So that is what we are saying. We are saying, I need the information on whether it is an error or not. If it is like so, give me what is the error value also. Okay, so how much of error has been faced there. Then we multiply it with the weightage. Why? Because if this is 2 units, but if this data point is given a higher weightage like 50, now 50 into 2 would have become 100. So this is where the weightage will come into play. So you are saying if the error value is 2 only, right? If there is a 50% weightage, 50 into 2 will become 100. But if it were only 10% weightage, 10 into 2 would have been only 20. So the reason for keeping Wi is basically to multiply it with the error value you get. So now you're saying, hey, I need to have the information whether it's an error or not. If it is an error, tell me how much of error. I will multiply it with the weightage divided by the sum of all the weightage, basically to sort of normalize it. Forget about this step. I'll tell you why it is. So we're just finding what is the error faced by this particular predictive model as a whole. So for every data point, you're checking whether it's an error or not. If it is an error, how much? Then what was the weightage given? Weightage into error will give you the total error for that data point. Add it for all the data point, that will be the error faced by the predictive model as a whole. So this is basically error of 1. So C1 of X is the model, error 1 is basically the error faced by that particular model. Okay. So now what have we found? We have basically created the model. We have found the error also. So we have error of 1 right now. What is the next step? The next step is to basically identify which of these people were misclassified and give them a higher weightage. Similarly, based on the error faced by the model, I need to come up with the model coefficient. Only then I can do a weighted average towards the last. So there are 2 steps pending. So I need to identify who got misclassified and increase their weightage so that in the next step he will make use of it and he'll make sure that they're not getting misclassified. And the error that you see here, based on it, you need to come up with the model coefficient. Why? Because you're basically saying using the model coefficient, I need to do an average here. That is why going back here, you guys can see, we are going to update the weights of the people who have got misclassified right now. So I'm going to clear the screen, guys. So you can see here, now we are saying, hey, update the weights for the people who have got misclassified. Sure. How can I do it? Once again, you're asking the same question. Can you please tell me if the true value is not equal to the predicted value? Of course, yes. I'll give you 1 if it were a misclassification or an error. I'll give you 0 if it were a correct classification. Why? Because you can see here, we are saying the new weightage for a data point will be the old weightage he had into exponential of alpha of the error that he had. Okay, the flag 1 or 0. Okay, I'll tell you what is this alpha. Just look at this equation, guys. So what are we doing? We're asking this question. Hey, is the true value not equal to the predicted value? Can you please let me know? I can give you the answers 1 and 0. 1 means yes, it's a misclassification. 0 means it's a correct classification. Now I will say, hey, the new weight is nothing but the old weight into exponential of alpha into the flag whether it was 1 or 0. So let us assume the alpha is probably 10 or something. Alpha is nothing but a model coefficient, okay? I'll tell you how we have estimated that in the next step. So let us assume it is 10 or something. So what is happening? You're saying, hey, the new weight is nothing but old weight was 10%, multiply it with exponential of, if this was misclassified, it would have been 1, exponential of 10 right now. But if it were correctly classified, it would have been exponential of what? Exponential of 0. So because 0 into 10 will be 0. So if it were misclassified, it would have become exponential of 10. If it were correctly classified, it would have been exponential of 0. So what happens in the second stage? Exponential of 0 is what? Basically 1, isn't it? Hope I'm not wrong. Suddenly I got confused. Exponential of 0 is what, guys? P of 0. 1, correct. So exponential of 0 is basically 1, isn't it? So what will happen is you are basically saying 10% of into 1. That is, the old weight is going to be equal to the new weight only. We are saying, hey, he did not get any misclassification and all. So let's leave it as it is. We need not give any increase in the weightage at all. But probably if you're assuming he got misclassified, now what will happen? Exponential of 10, which will be a pretty massive number. Okay, what is exponential of 10? 22,026. Now you are saying, hey, it was already 10%, okay? Now multiply it by 22,026. Now it will become a much more bigger number, right? 2.2 into 10 to the power of 5 or something. I'm just assuming it would have become much more a bigger number. That will become the new weightage right now. So the old weightage what you gave was just 10. Now you're saying multiplied with the exponential of this error component and the alpha that is involved, it will become a higher weightage right now is exactly what we are saying. Thereby what have you done? You have basically identified which people have got misclassified and you've given higher weightage for them right now. What do you also need to do finally, as I told you all, based on the error, you need to come up with a model coefficient, isn't it? You need the model coefficient. For that, now we have an equation. So the equation is basically step number 3. We are saying, hey, model coefficient is nothing but log of 1 minus error divided by error. That's all. Okay. So we're basically finding what is 1 minus error divided by error. That's it. So this will basically help you find the model's coefficient. Why we are using log is because it'll be very smooth. That is the reason why we are using log. So the coefficient should not be very drastic. So you can't tell me that 5% of accuracy, 20% of accuracy. I'll give a model coefficient like 10%, but I'll give a model coefficient of 80%. You can't give such a drastic result. You're saying give coefficients which are more smoother, like 10 or 30. You can say much more smoother coefficients is what we want. We don't want a sudden change is exactly what we're saying. So alpha of m is basically going to be the model coefficient you'll come up with based on the error faced by the predictive model here. Okay. So we are initializing all the observations with equal weightage. We are creating a model with the equal weightage. We are finding what is the error faced by the total decision tree. Because based on that, I need to come up with my model coefficient. Then I need to go back and find who are the people who have got misclassified. Those data point weightages has to be increased right now. The other people will be left as it is. Now this new set of weights will be used by the second classifier. He will find what is his error. He will find his coefficient. He will update the weights and leave it for the third model that you're going to create. The third model will evaluate how much error he is having. He will find his coefficient. He will update the weightages as per his error and he'll leave it for the fourth model here. Fourth model is getting created, his error, his coefficient, he will update it. So this keeps happening in a cyclic fashion till the m number of models that you want to create will basically get created. So everybody is looking into what is happening at the previous stage here. So you can see it's actually a stage-wise addition. So what you're saying is, initially I will keep it as 0. I will write a for loop, and now I will say, you can see here guys, we are finding the error between, L is called as loss, okay? L is loss, or also called as error, between the true value and the predicted value. How can I come up with the predicted value? Let us assume we are in iteration number 2, okay? We are saying the predicted value is nothing but the prediction coming from the previous stage plus the prediction coming from this particular stage, but I need to basically multiply it with a small coefficient and then add it here. This is the error. So every model that you create is an improvement over the previous one, is what I'm saying, right? So the first case would have been what? Yi cap is equal to 0. Okay, y of 0 I'll say is 0. Y of 1 is basically what? F1 of x you created. Y of 2 is what? It is basically y of 1 cap plus f2 of x. Y of 3 cap is what? Y of 1 cap plus f3 of x. But if you ask this question, who is y of 1? Sorry, y of 2, right? Y of 2 is nothing but this guy. Who is this y of 1? It is this guy. So it is actually f1 of x plus f2 of x plus f3 of x. It keeps going on and on. It's a stage-wise improvement. So you can see it here. So yi cap of 0 is 0. In the first stage is nothing but first model you created. Second stage prediction is first stage prediction with the second model that you created. It will keep happening over and over again. It's a stage-wise addition that you keep doing, right? Then you're asking, okay, what is the error faced in this particular stage altogether? This error I'll try to improvise in the next stage. What is the error faced at this stage also including? I will try to improvise it at the next stage. It keeps happening over and over and over and again, right? So this is exactly is the boosting algorithm here, guys. We are trying to improvise it at every fashion here, at every iteration here. But an important point to notice is while you're improvising it, right? So you don't pass it completely, only like a small weightage of it will be passed here, okay? So you're not saying that complete improvement will be passed on, only small improvement of it will be passed. So there is a learning parameter that is typically involved here, okay? So basically you're saying not this guy, he is not the learning parameter, he is the learning parameter. This is the model coefficient, okay? This is the learning parameter. So you're saying even after doing that, model coefficient and multiplying with the probability, right? We'll say that not complete improvement will be passed on, only a certain amount of it will be passed on. So there is a learning parameter that is typically kept. So don't worry about the learning parameter. I'll come back in a minute. Before that, is all this okay? Starting from initializing equal weightage, creating the model, then going back and finding the error faced by the model totally, then coming up with the model coefficient, then coming up with the individual data points coefficient. So in this fashion, you keep creating different models. Now the third point that you have is the prediction point that we spoke about. So what is he doing? He's giving the input to every model that you see. C1 of x, C2 of x, C3 of x goes on. And the prediction coming from each and every stage will be multiplied by their alphas. So multiplied by alpha 1, multiplied by alpha 2, multiplied by alpha 3. So alpha into the CM of x will give you the final prediction is what we are saying. So this is your final prediction here. So now tell me guys, are you all okay with this particular algorithm? Does the story and the algorithm coincide or not? Yes or no guys? Were you all able to follow? Yeah. Okay, cool. Perfect. So this is everything that you need to, understand about a boosting algorithm, guys. I'll tell you the other boosting algorithms that you see are all basically improvements over the previous ones. Okay. I'll give you an example. So say an example. So you said, hey, I want to create the new decision tree, which is an improvisation over the previous one, correct? So basically the equation will come out like this. You'll say, hey, this is the prediction. This is the new model I'm creating. Along with that, I will get the true and the predicted value. This error should keep coming down, right? So you're saying it should be an improvement. So how can I make sure that it's an improvement? I need to design the decision tree in such fashion, right? This is the only place where there will be changes, guys. That's all. Say for an example, in XGBoost, the way they solve it is in this fashion. You can see. This is an algorithm for XGBoost, okay? You can see here, same thing, whatever we spoke of. What do you see? L. L stands for loss. Loss between true value and predicted value. What is predicted value? All prediction till the previous stage plus the prediction coming at this particular stage. So prediction till the previous stage plus the prediction at this stage. This is your true value. This is your predicted value, correct? So the error between this guy should be lesser. That is what we know. That's what we're doing. Now, how to solve this is exactly where gave birth to different XGBoost implementations. So you have GBM, which is actually using something called gradient boosting method to solve it. You have something called XGBoost, which is using extreme gradient methods to solve it. You have CAT boost, then you have something like light GBM. So this equation solution is basically what is going to differ, guys. But otherwise, the framework is the same. No changes to the framework at all. See here, this is how XGBoost is actually solving. He's using something called Taylor's expansion. So a Taylor's expansion will kind of approximate the original function with a sort of a polynomial like this. Then you can go back and differentiate it as you like. So this is different methods that people will kind of adopt. So you don't have to go on the inside and ask the question, how are you solving it? Right? Even if you take the linear regression, right? We spoke till how the loss function is coming, but how did you solve it? I solved it with Excel. I solved it with Python. I solved it with R programming. All of us use different methodologies. That is the answer you're telling me, right? Similarly, logistic regression, I know up to the loss function. I understand what's happening. How did I solve the logistic regression? One guy was using Newton-Raphson method. One guy is using some other method. We don't have to go back and dig into what different authors are using to solve those equations. Same thing here. XGBoost, CATBoost, GBM, they're all saying, hey, we are all different people with different kinds of methods of solving these equations. Using our methods, we are differing in our accuracies a little bit. So XGBoost will give you couple of notches better accuracy over GBM. Then CATBoost and Light GBM are also equal competitor to your XGBoost. Sometimes they can even do a little better. That's it, guys. So this is basically differentiating on the method on how they are solving their loss functions. That's all. Which we don't have to go back and deep dive on how are you solving it, etc. It's not very important for us. Okay. So this is exactly how a boosting algorithm is typically getting created. And now, by now, you would have understood how is it different from all the previous Ensemble implementations that we have discussed till here. Right? So what I will do quickly is that, guys, we're going to take a minute to go back and implement this XGBoost here. Okay. Before that, let me introduce you all to something called as log loss, because I think we're using log loss in evaluating every stage of the model. Okay. So let me just quickly talk about log loss. I think it's an equation we've already seen. Okay. So if you all remember in logistic regression, we spoke about log loss. I mean the logistic regression's equation is called logistic loss or log loss. So what is the equation? Yi times log of probability plus 1 minus yi times log of 1 minus probability. That's all. So when you add a negative at the front, it becomes log loss. It will be a positive answer. If you don't keep the negative at the front, it is how we solve the MLE. So we are keeping a negative at the front. This is called as log loss. So the more and more far away are the probabilities from the true values, the more and more will be the loss or the error value. Correct? So going back here, I think we were talking about the digit recognizer problem. Correct? So what we will do right now is we'll quickly create a decision tree. Okay, so we are creating a decision tree here. So we're going to ask what is the log loss. The log loss faced by a decision tree model has been 5.2, which is one of the worst models you can create. Okay, the probabilities are what? It's probably hanging in 60 or 40 somewhere, even though you have a good accuracy, right? They are not very confident in their predictions. The log loss is all pretty high, 5.24. I think we had a good accuracy like 100. That was fine. But look at the log loss. You can understand that they are not very confident predictions. Even though the predictions are right, it's not so confident. That's why you got a log loss of 5.24. Then let's go back and create a bagged decision tree. I think it's here. We'll quickly create a bagged decision tree. Okay. So it has to create 5 decision tree models, 5 predictions, and we'll basically do a plain average. So let's just wait for him to complete, and then we can check what is the log loss he is having. Okay. So as I told you, the accuracies might be good. So it's a good model if he says I'm 95% confident it's a digit 0, rather than saying I'm 55% confident saying it's a digit 0, right? So now look at the log loss. We have got 0.05. Just by creating 5 decision tree models, can you see from somewhere like 5.24 you have come to 0.05. Now do you guys agree why I'm saying a single decision tree is too bad compared to how a bagging model will actually work? Let's go back and check with the random forest. Let's quickly create a random forest. 200 decision trees is too low, but still it's okay. Let's still create it. We're going to go back and create this guy. Let him create. Okay, so we need the predictions. Where is my predictions space? Okay, so it's going to take a couple of minutes. Yeah, it's done. So now we can ask for the log loss. It's 1.53. Why? Because you know it, right? The number of estimators here are too low. We need to increase the number of estimators. Okay, then it should be ideally good. So then over to boosting model that we have here at the bottom. Let's go back and just hit Control Enter. So let me take you all through the boosting model. So see here, guys. From scikit-learn.ensemble, we're importing gradient boosting classifier. Control Enter. We are saying, hey, gradient boosting classifier, you have 500 estimators. So let me hit Control Enter. Let it keep running. So we are saying I want you to create 500 models. The learning rate is 0.1. What do you mean by a learning rate? Very simple, guys. So here you can see we are saying, hey, this is the previous stage. This small b equation is my current stage. This beta of m is my model coefficient, correct? You're saying instead of passing the total probability as it is or the total prediction as it is, let us use a learning rate, no, some small decay parameter. So what you're saying is f1, f2, f3, f4. Okay, f1 is probably having 20% accuracy only. Then if you have a model which is giving you 50% accuracy, now what is the average? Average would have been something like 20, 30, difference is 15, so 35% accurate, correct? But we're saying, hey, instead of using the f2 as it is, by utilizing all the 50%, utilize only 30% of its accuracy. We are decaying it a little bit purposely. Why? Because we are saying, let us go back and create many predictive models now. We don't want to become stagnant just by a few models. Let's kind of reduce it. We are decaying the accuracy a little bit purposely. Now 2030, what is the average? It would have been only 25% or something. Then include the next guy. He says I have 80% accuracy. Now you can see 25, 80 and all, the average would have been, let's say, 50 or something. But you're saying no, don't give it as it is. Decay yourself a little bit. Give only a 50% accuracy. Then you may probably end up with 45. It's more like minor improvement. You want a minor improvement happening at each and every stages. So one guy should not say, hey, let's move in this direction. Another guy shouldn't say, hey, let's move in this direction. Another guy will suddenly ask you to move in this direction. We are saying, I don't want such drastic movements. I'm going to move pretty slowly. Okay, I just want like slow movements in getting the best model. I don't want such very fast movements here and there. I don't want the accuracies to keep going up and down pretty massive. Let's take up small improvements. That's what is called as learning parameter. So we are giving a learning parameter of 0.1. Even if the model's accuracy is going to be pretty massive, we are taking only 10% of it. Then what are we doing? We are creating a train test split and all. Train X, train Y is here. Then what we are doing is we are taking the test Y, we are converting it as dummies, then we're going to predict it. This will give you something called as log loss. Let's check what is the log loss we are getting. I think this is going to take a lot of time. I remember it always takes a lot of time. Okay, so let it keep running. So I think with this one, we are kind of done with boosting also. So we understand how a random forest model will work. We understand how a decision tree model will work, even a plain bagging model. So we understand that bagging is any day better over a decision tree. Random forest is any day better over decision tree and bagging. Boosting is any day better than random forest and other people, right? In fact, boosting can give a very tough fight to even neural network models. Okay, so if you tune the boosting models properly, right, they can give you even better predictive power compared to neural networks. Okay, so that's why boosting is a very important class of model that you need to understand, and that's exactly what we have discussed till now. Okay, so any questions still here, guys? Are you all convinced how it's working? Yeah. Great. Okay. So what we can do is, I think we can probably go for a break. Okay, so let's go for a 15-minute break probably. Okay, then we'll come back. Meanwhile, the GBM will also complete. Then we'll jump into neural networks. And what I will do is, guys, I have a use case. Okay, there's a home credit default use case. Basically, we are trying to create something called probability of default model for a financial institution. They're basically some mortgage loan lenders. So we'll go back and create a model for these guys, and probably once we'll complete a neural network, I don't think we'll be able to do it today. So probably tomorrow or something, we can jump into the use case and we can apply all the models that you've discussed till now. Okay, so we'll speak about each and every data set. We'll do some feature engineering. We'll start creating the different models that we have discussed till now. So that is going to be the agenda next. So next we'll jump into neural networks, then over to this particular use case here. Okay. So the use case for XGBoost, sorry, the GBM, etc., should be this particular home credit use case that we are seeing. I think let's go for a quick break. So let's be back, let's say at 6:30, shall we? I think it's going to be a pretty long one, 17-minute break. So let's be back at 6:30. Then we'll jump into neural network models. I'm pretty sure it's going to be very interesting. And probably by tomorrow, when once we complete, we can jump into that particular use case. Okay. Great. So let's take a quick break, guys.
This conference will now be recorded.
Okay, cool. So let's get started. So the next topic that we're going to be discussing is basically deep learning. Okay, deep learning or artificial neural networks. So however you may call it as, right? So it's a very interesting topic, guys. It's a beautiful topic also, I'll tell you. I want to make sure that somehow it's like very interesting for you all. You know, I'll make sure that it's something that you all can follow it also. So what we have here is basically a concept of something called as artificial neural networks. So the first question that will strike our mind is, what exactly do you mean by artificial neural networks, correct? So what do we have? We have ANN, or otherwise something called as artificial neural networks. The first question is, what exactly do you mean by artificial neural networks? I think all of us might have done some research on what is ANN, what is deep learning, everything, isn't it? So all of us know that, you know, basically this ANN or the deep learning is a model where the researchers were trying to mimic how a human brain is basically going to work. So what do you have in human brain? So you have basically something called as neurons, isn't it? So the neurons are basically connected to different other neurons, right? Which I think we call it as synapses and all. So every neuron has this component, something like axon, dendrites, and things of that sort, correct? And whenever information is getting passed on from one neuron to another, it's all chemical firings. So you might have seen Avengers movie and all, right? Where you would have seen that, you know, Age of Ultron movie. So you would have seen Ultron, that blue color network, or the orange color network you might have seen, which is actually Jarvis, right? So they're basically trying to imitate how a human brain works. So as you all know, human brain is all connected with a lot of, you know, neurons here and there, isn't it? So it's all connected with a lot of neurons, right? So what are we doing? We're basically saying, okay, let me pinch the hand of some person. Then, you know, one of the, you know, neurons is going to get kind of fired. Then he will pass on the information to all the other people. Then it becomes like an action. What you do is typically you know, try to retrieve back. So this kind of a pattern that they saw in human brains is exactly what people wanted to kind of imitate. And that's when they started creating something called as artificial neural networks. So let's please understand, guys, in artificial neural networks, the most important class of model is something called MLP, which stands for multi-layer perceptron. Okay. So what do we have? We have MLP, or something called as multi-layer perceptron, who is actually speaking the predictive unit of this entire artificial intelligence. So tomorrow you guys might get introduced to something called CNN, convolutional neural networks, or you might get introduced to something called RNN, recurrent neural networks, or and versions of CNN like RCNN, etc., etc. I mean, these are all not predictive models, okay? So what a CNN will do is, it will basically take up a high dimensional data set and it will convert it as a small low dimensional data set. That is the work of CNNs. Basically, they help you extract features. What is RNN going to do? The RNN is going to basically understand sequences. So they are not predictive units. Still, even if you want to create a CNN model, you need to use it with a combination of MLP. If you want to use the RNN model, you still need this guy, something called as multi-layer perceptron. So don't worry about the second things, guys. Just understand that this multi-layer perceptron is actually speaking the most important predictive unit, or he's the only predictive unit itself, I would probably say, in this entire class of deep learning models that we see, the artificial neural network models. Now the question you might probably have is, what do you mean by multi-layer perceptron? What is this predictive model all about? So multi-layer looks like he's creating multiple layers of what? Multiple layers of something called as perceptron, right? What exactly do you mean by a perceptron? Guys, the perceptron, or basically a neuron, is the fundamental unit of your artificial neural network, typically depicted something like this around here. So what do we have? The perceptron or the neuron is the basic unit or the fundamental unit of your multi-layer perceptron models here. What is this perceptron actually doing? Very simple. The perceptron is actually nothing but equivalent of a linear regression model, or sometimes even a logistic regression model. A perceptron is actually speaking a linear regression or logistic regression model. More like 90% it's a linear regression or a logistic regression model only. So this perceptron, guys, he will basically need an input, okay? And what he will need is, he'll also need another guy, somebody called as a bias, as an input. While taking the input here, he will have something called as a weight, a connection weight, and then he will compute something and he will give you something called as an output. So what do we have? We have an input, then there is a small connection. The connection will have a W weight. Then you have a bias, which is another input this perceptron will take up. Then he will compute something and he will give you an output. Otherwise, to write it in terms of an equation, output is nothing but input into weights plus bias. That's all. Or y is equals to x into w plus b. That's all. But another beautiful add-on that the neural network or the perceptron here is having is, he's having another small block here, which we call it as an activation function block. So this is called as what? This is called as an activation function block. You're saying, hey, output is not just input into weights plus bias. Sometimes you can apply some function also. That's all. So y is basically equal to what, guys? It is equal to f of x into w plus b. X is the input, w is the weight, b is the bias. When you do x into w plus b, you get an output which might be passed on to any function that you like here. Now tell me, guys, looking at this core area, doesn't this resemble a linear regression model? Beta naught plus beta 1 times of x, isn't it? Doesn't it resemble a linear regression model here? So this piece is nothing but a linear combination of variables. Input into weights plus bias is basically a linear combination of variables. By applying some function, you can make it as non-linear also if you want. So the core perceptron is a linear thing. After applying a function, you can make it as non-linear. So I will get an output like this. So 20 times 3 plus 10, this is linear only. The result is basically what, 60, 70. Now I can make them as non-linear by doing something. Example, for an exponential of 70 or something. So it will become non-linear. So this core piece of doing input into H plus bias or X into W plus B is nothing but a linear combinations of variables. Just by applying this particular function, you're making it as a non-linear output here. F of X into W plus B plus bias. This is exactly what is called as a perceptron. And now I'll tell you guys, this single perceptron is itself a single predictive model that you're creating. It's a single model that you're creating. So what are we saying? We're saying it's a single predictive model here. That's all. So what we can probably do is we can create many predictive models and we can start ensembling them. That is when it will become a multi-layer perceptron. So I'm saying, hey, this is one predictive model. There's another predictive model. There's another predictive model, right? So you can see, right? The boosting was doing the same thing. He created decision tree 1, decision tree 2, decision tree 3, 4 and 5. Similarly, here he's saying, I'll create perceptron 1, perceptron 2, perceptron 3, 4 and 5. I am basically nothing but a linear regression model. Sometimes you can make me as logistic regression. You can make me as any model you write. I'm just creating many models here all together, which I'm calling as ANN or a multi-layer perceptron model. So this is one layer. This is another layer, the third layer, fourth layer, fifth layer here. This will become a multi-layer perceptron model here. So just imagine, guys, what is a neural network? A neural network is basically a collection of a lot of predictive models. That's all. That one single perceptron itself is a predictive model. You just have to imagine creating so many perceptrons, which is equal to so many predictive models, getting the result from all those predictive models, which is nothing but the ensemble of models that we've been discussing today. Right? So don't worry about the MLP. We are not yet jumping into that discussion. We have still not done with a single perceptron here. We have understood that the single perceptron that we see here is the building block of your artificial neural networks, written as f of x into w plus bias, where x is your input, w is called as weight, b is called as bias. This f is nothing but an activation function, and there are several activation functions available here in deep learning models. So what we're going to do is, guys, we're going to go back and implement neural network models in Python. Okay, so I'll tell you all, in scikit-learn you have neural network models. Of course you can create MLP in what? In scikit-learn. But the point is, in scikit-learn, creating MLP doesn't give you a lot of customizations. There is not much of customizations you can do, unfortunately. That is why today people have started migrating to things like TensorFlow or something like Theano or something like Keras. Okay, so people today have started migrating to something called TensorFlow or Theano or something called Keras. Now talking about this one, I'll tell you guys, TensorFlow is literally just a plain computational library. What is TensorFlow? It's literally a plain computational library, which means it's a library that you can probably use for creating even statistical models or machine learning models, deep learning models, or you can use it for optimization purposes, or let's say you can use it in any other area, any other field of mathematics. It's a literal computational library. You might have seen NumPy, isn't it? Very similar to NumPy is this particular guy, TensorFlow. Very simple computational library. It's not a deep learning library. There is a very common misconception, or even I don't know. Even probably Google is doing it. Even Google is trying to push it as a deep learning library, but it's not so. It's a computational library used popularly by deep learning people. That's how you need to think of it. The same thing goes even with Theano. Theano is also a computational library which has been available since years. It has been used for creating statistical models. You can use it for machine learning models, deep learning models, for optimization, for any purposes you can use these people. But Keras is a library which is specifically only a deep learning library, which means I can't expect to create a ML model like random forest or boosting, right? Or I can't expect to create, let's say, some optimization algorithms like simulated annealing. No, I can't do that. So TensorFlow or Theano, they are Python libraries which are computation libraries because they give you all the functions available to do any task you want. So what I can do is I can go back and create a perceptron in 4 lines of code, where in Theano or TensorFlow, how will I do it? I'll go back and say, hey, A is equal to np.tensor, sorry, I'll just say tf.tensor. So we are saying it's a numpy array, equivalent is tensor. Then we will say, sorry, x, okay, w, b is also a tensor. Then we will say x into w plus b. Okay, I'm just assuming. So this is how it will work. So you need to go back and write each and every line of code. So what he has to do? Okay, so x is basically nothing but one tensor. W is another tensor. B is another tensor. Go back and multiply them. You are creating a perceptron using 4 lines of code in Theano or TensorFlow. But in Keras, it's a single line of code. It's a 1-line code. Why? Because Keras has been built on top of TensorFlow and Theano. It is like the difference between C programming versus Python programming. Do you know that Python programming has been written on top of C? Right? We call it a C Python. In fact, there's another level of Python that you can write, something called C Python. So the Python code is nothing but C at the back end. The C gets into a machine level language and it goes on, right? So Python is getting translated as C, then that gets translated in machine level language in the same fashion. Here Keras is a 1-line Python code I will write, where he will have 4 lines of Python code at the back end. So Keras will go and construct the TensorFlow or the Theano codes for us, which means you don't have to go back and write TensorFlow codes or Theano codes, which is going to be pretty verbose. I'll tell you guys, in 99% of your deep learning models, right, you can surely accomplish it using Keras. It's only certain models, certain researchers or academic people who want to come up with an entirely new structure. It may not be possible too much in Keras. You may need some customizations. They may go to TensorFlow. But still, you can somehow do it in Keras. I think 99% of the cases you can do it in Keras. Probably 1 or 2 cases may not be possible in Keras. You may have to go back to TensorFlow. So my point is, you don't have to know TensorFlow. Even I don't know TensorFlow. Theano also the same thing. I just know a very basic understanding of TensorFlow and Theano. I haven't coded much about it, but Keras is something that all of us should be well versed with, because that is going to help in all of the models that we want to create. So 99% of the cases, guys, Keras is going to be pretty helpful for us. It's only in certain odd cases TensorFlow or Theano might be required. So whatever you write in Keras is going to get eventually translated into a TensorFlow or a Theano code by the end of the day. Okay. So this is the point that you all need to understand. And in our course here, we're going to be discussing about Keras, exclusively. So what I will do is I will pass on the instructions on how to install Keras. I think most of you will say, going back and doing pip install of Keras will do the job. Yes, of course, it will do the job, but there are a lot of compatibility issues. Some version of TensorFlow will only go with some version of Keras. So I have tested certain versions. I have found that in TensorFlow, there is like 1.1 something, and Keras there is 2 point something. There are certain versions which are pretty compatible. There are not many errors. So I will pass on to you guys on the instructions on how to create your deep learning environment. Okay, so I'll be passing on an environment file, and I'll be passing on a PPT. It will give you the steps on how you can install your deep learning environment here. Please do follow that. Don't go back and install Keras by using plain pip. Don't do it. There's going to be a lot of compatibility issues here. Okay. So this is with Keras. Now what you're going to do is, guys, coming back to the perceptrons theory, we have spoken about perceptron and we understand that it is a fundamental unit in your multi-layer perceptron, which means That single guy himself is a beautiful predictive model. Now what I'm going to do is, guys, I'm going to help you all understand why is a perceptron almost equal to a linear regression? Why is he almost equal to a logistic regression? Or vice versa, can I implement a linear regression model using a perceptron? And can I implement a logistic regression model using perceptron? This is going to be the point of discussion right now. So let's go back here to linear regression. So I'll quickly take you all through the data. So what we're doing is we are importing NumPy as NP, Pandas as PD, and scikit-learn. Okay. What we'll do next is we'll go back and import a data set. Okay. So this is weight and height data set. I think we might have probably discussed this already. Right. So we are basically taking up the two variables, which is height and weight of a person, and we can see that it is completely linear, which means it's totally capable of creating a linear regression model here. You can perfectly create a linear regression model here. Now we are saying, hey, capital X is nothing but the height, capital Y is nothing but the weight. Control enter. From scikit-learn import linear model dot linear regression. Now we'll go back and say, yes, it's a linear model, linear regression type. Fit X comma Y, coefficient is 7.71, intercept is -350. This is the result that we have got by creating a linear regression model using scikit-learn here, right? So using scikit-learn, if I were to create a linear regression model for this data set, this is the result we will have, 7.71 and -350. Now what we're going to do is, we're going to come down here, okay? So this is something very interesting. I don't think we discussed this in our previous sessions. So see here, guys, in the other day while we were discussing about linear regression, right, I told you all that there are a lot of possible combinations, isn't it? But whichever combination is giving you the least error is the best combination, correct? So here we are doing a simple simulation and we are generating a lot of possible combinations, okay? So you can see here, we are generating different possible combinations. We are creating so many models. We are coming up with the error value and we're keeping it here. So you can see here. So we are using 1.0 as a weight, minus 200 as a bias. 1.0 is a weight, minus 190 as a bias. So we get different errors. When we come down here and create a 3D plot of it, this is exactly how the error curve will look like. Okay, it's going to look like a U-shaped curve, something like that. So basically the optimization is something called as a convex optimization. So you're saying in every other point, the error will be high. Only at this particular point, the error will be low. So there is one single solution only, which is called as a convex optimization here. So our role here is to what? Is to use Keras and implement a single perceptron and imitate how a linear regression model will basically work. So what we're going to do is, guys, see here, I'm just checking if Keras is available. Okay, looks like Keras is available in my environment. He is using TensorFlow at the backend. So any Keras code that I'm going to write, right, will basically get converted as a TensorFlow code at the backend. It will merely get translated as a TensorFlow code at the backend. So we are totally happy. So now we can go back and say, from Keras, can you please import something called sequential? You're saying, if from keras.models, can you please import something called sequential? Very simple, guys. In Keras, there are two kinds of APIs that we need to understand, or two methodologies of creating a neural network model. The first method is by using a sequential API. The second method is basically using a model API. So what is the first case? The first case is a sequential API. The second case is basically a model API. What do you mean by a sequential API? Very simple, guys. See here, we will say, hey, create a model object who is of a sequential type. So we are saying your right now sequential type. What do you mean by a sequential type? We are saying every perceptron I'm going to add, right? So every perceptron that I'm going to add is going to be added in a sequential fashion, which means going back here, we are saying this is my first perceptron, correct? He is saying, I will give you input. I will have a weight. I will have a bias. What will I give you? I will give you output. So the output here is what? Y is equal to x1 into w1 plus b1. Then what we are saying is, this will serve as an input to another perceptron. He will have his own weight connection. He will have his own bias also. So he will give you outcome which is y of 2. So y of 2 is nothing but your y of 1 that you've got in the previous stage into w of 2 plus b of 2. I hope everybody is on the same page. Let's go again. See you guys. He will give you output, isn't it? Which is y. What is y? Y is equal to x1 into w1 plus b1 is what we are saying. This will be given as an input to another perceptron who is having a weight connection of w2. He will also receive a bias value which is b2. He will give you an output which is what? Which is y2 right now. What is y2? Y2 is nothing but the output coming from the previous stage, which is y1 into w2 plus b2 over here. So what are we saying? It is y1 into w2 plus b2 is exactly what we are saying. This output will now be passed on to another perceptron through a connection like w3. He will have a bias like b3. He will give you output which is y3. So you're saying, hey, y3 is nothing but y2 into w3 plus b3. So you can see. So he is computing an output which is y1. This will serve as an input to the next guy. He will compute an output which is served as an input to the next guy. He will compute an output which becomes the final output that we are interested with. So they are all connected in a very sequential fashion, isn't it? So it's all coming one behind the other. So the order is very important. It is happening in a very sequential fashion here, correct? That is why we go back here. We say, hey, model is equal to sequential type. Now we are saying model.add, can you add a perceptron 1? So we are saying, hey, can you please add the perceptron 1? Just behind it, can you please add perceptron 2? Sure. Behind that guy, can you please add perceptron 3? Then what we're saying is, we are saying, hey, model.fit, this will be my x and this will be my y. That's all. So whenever you say it's a sequential, and the next add and all that you're seeing, right? So this add, if it gets executed, it's layer 1. This add will say it's layer 2. This add will say layer 3, and you keep going on and on and on. So in a sequential API, all the adds that you're doing, right, they will all basically happen in a sequential fashion, one behind the other. That is something called as a sequential API. What do you think is a model API? Model API will help you create non-sequential models. Say for an example, somebody might design a network like this. They will say, okay, let us have one input perceptron. Okay, input. He will compute an output, y1, correct? He's having what? w1, he's having b1. So he will compute what? y1 is equal to x1 into w1 plus b1, correct? Now what we're saying is, instead of adding one perceptron, let's branch out to two perceptrons. So there is perceptron 2, there is perceptron 3. What are you saying? You will have weight 2, you will have weight 3. He will have bias 2, he will have bias 3. Now you are computing y2 is equal to y1 into w2 plus b2, but here you're doing y3 is equal to y1 into w3 plus b3. So it is not in a sequential fashion, right? So he is branching out here, he is branching out here. I can't add the two perceptrons one behind the other. No, it's not wrong. Sorry, it's not correct. It's wrong. It's not in a sequential fashion that we want. We want it in a non-sequential fashion. So if you need it in a non-sequential fashion, guys, you basically need to make use of something called a model API. So what's required? You need what is called as a model API. In a model API, you will basically say, hey, let us say A is equal to layer 1. So let us say A is equal to an input. I'll say A is an input. Okay. Then we will say B is equal to a perceptron. Okay. But he will receive the input from A is what we are saying. Similarly, we will say, hey, B is also another perceptron, but he will receive, sorry, C. Okay, C is another perceptron, but he will receive his input not from B, but from the original A right now. Getting what I'm saying? So we're saying A is an input. Okay, so let's design this network itself. So A is an input, B is a perceptron. This will give you an output. Okay, now we are saying C is the perceptron, D is also another perceptron, but the input of C is basically coming from B, and the input of D is also coming from B. Right? So A is the input that somebody will pass. B is a perceptron you're creating. He will need the input into H plus bias. He will compute the output. This output will go as an input to the C perceptron as well as the D perceptron. So it is not in a sequential fashion, it is branching out here. This is the difference between using a sequential API versus a model API. Once again, I'm telling you, most of your cases, 90% or 80% of your cases, you will always need a sequential API. You won't need a model API. So that is what we're doing, guys. Going back here, I'm saying, hey, from keras.models, I want you to import the sequential API. Sure, why not? I can do it for you. The next thing that you all need to understand is the perceptrons that you're adding, right? In every layer that you're adding, right? You have a layer name, by the way. Okay, it's not as simple as it is. You're going to say that the layer I'm going to add is a dense layer. There is a layer name that you give. The layer is basically something called as a dense layer. Within this guy only, you say, I need one perceptron. I need 10 perceptrons here. And here you'll say, hey, there is another dense layer. I need only 3 perceptrons. So at every layer you're adding, right? What layer do you want me to add? You can add a dense layer. You can add an activation function layer. You can probably add an output layer. So any layer can be added. We are saying, hey, it's a dense layer I want you to add. In that particular dense layer, we're going to add a perceptron. So we will say, hey, I need one perceptron here. Hey, I need 10 perceptron here. I need 5 or 3 perceptrons. So the kind of layer that you're going to add is also pretty important. So we are adding a dense layer there on the inside. For that, we need to go back and import that guy also. From keras.layers, we are importing something called as a dense layer here. So from keras.models, we have imported sequential because sequentially we're going to be adding one layer at a time. What layer are we going to probably add? We're going to add a dense layer here. That's why we're saying from keras.layers, let's import dense layer. I'll talk about those optimizers probably in the next class. I don't think we'll have enough time to even jump into the optimizers if I'm not wrong. Okay, let's see. So there's something called as an optimizer we are importing. So what is an optimizer is? Basically, it is a solver. In Excel, you all remember, right? You have what solver method do you want to do? There is a question. So if I go to data, you can go to solver. He's asking, right? What solving method do you want me to use? Do you want me to use GRG nonlinear or simplex LP, linear programming, or the evolutionary algorithm? It is asking you what method to probably use and solve it, isn't it? That method is the optimizer that we're talking about here. So the optimizer here is basically what method should be used to solve it. Similarly, I told you here, right, in the XGBoost thing that we're talking about. So in this equation, we said, hey, this is an equation which is common, isn't it? So the objective is nothing but loss between true value and predicted value. But how to solve it? So here he used a Taylor expansion and he started finding the gradient. Somebody might use Newton-Raphson. Somebody might use something else, gradient descent. So there are different methods of solving, right? That method is exactly what we're talking about here. The optimizer. I may use any optimizer and I can solve it. So here we are importing an optimizer called Adam. It's one of the most, sophisticated or pretty comprehensive kind of a person who can give you a good solution. So we are importing somebody called as Adam right now. So let's go back and hit Control Enter. We have imported the sequential layer, we have imported the dense layer, and this optimizer, something called Adam. And the math behind it, we'll jump probably tomorrow. I don't think the time might be enough to jump into today. Now you guys can see here, we are saying, hey, model is equal to sequential, sure. Then we are saying model.add, I want you to add the first layer, where it's a dense layer I want you to add. What layer are we adding? We are adding a dense layer. So you can have even an activation layer. So there's a layer, something called activation layer also you can add. Okay, but anyways, within the dense itself, you can keep any activation you like. You don't have to separately import it. I'm just saying there are several layers you can add. I can have an input layer, right? If I'm using model API, there's an input layer, there is an output layer, then there is an activation layer, right? There is a regularization layer. So different kinds of layers, but we are right now worried only about a dense layer where we can keep adding perceptrons. Control Enter, import, model is equal to sequential, model.add, add a dense layer. How many perceptrons do you want me to add? It's a single perceptron. Why a single perceptron? Because the work of a single perceptron is to do input into weights plus bias, which is equal to the linear regression model, isn't it? So we are saying, hey boss, I want to imitate how a linear regression model would work. Sure, for imitating how a linear regression model would work, you would just need a single perceptron. That's why we are saying, hey, it's a dense layer. Okay, within that we are saying it's only one single perceptron I want to keep, because that one single perceptron will just do the input into weights plus bias that I wanted. And then we are saying, hey, input underscore shape is equal to 1 comma blank. So 1 basically means I have a single column, but I will have a lot of rows. Okay, we are saying it's a single column. I have a single feature, but I will get a lot of data points for you. That's why we are keeping it as a blank here. So model.add, add the first layer. The first layer is a dense layer. The parameters that you're passing to the dense layer is number of perceptrons is 1. And only for the first layer, you need to specify what is the input shape. Only for the first layer, you need to pass what is the input shape. So we are saying input shape is 1 comma blank. So 1 basically means it's going to be a single column, but for a lot of data points. A single feature, a lot of data points. So we're just hitting Control Enter. The first layer might have got added right now. Then we are saying, hey, compile the predictive model. So he's going to convert it as a TensorFlow or a Theano code at the backend. If you don't compile, it won't work. Okay, I'll not compile it right now. I'll show you. So we are saying model.compile. So convert it as a TensorFlow code. How do you want me to solve it? Solve it using Adam optimizer. How do you want me to, compute the error? Compute the error using mean squared error. So I want to see how is the mean squared error working at every time you're going to improvise it. So let's not hit Control Enter for now. I'll just go to model.summary so you guys can see the model structure. He is saying, hey, this is the total model structure. Sure. He's telling us, for now, you have introduced only one single dense layer. So what is the layer type? It's a dense layer. And he's saying, what is going to be the output? The output was supposed to be input into weights plus bias, right? So the output is basically going to be what? It's going to be input into weights plus bias. Okay. So what is the input you have right now? You have a single column of data. So you have a single column of data, right? So there are probably 1,000 people's height values. So 1,000 into 1. You need to basically multiply it with the weight values here, isn't it? So it's 1,000 into 1. This 1,000 into 1, or it is W transpose X plus B. Typically, it is not input into weights. It's W transpose X plus B. Correct. Okay, when I mean by input into weights plus bias, in matrix notation, it will come like this. Okay. So X is what? X is basically that one single column that you will have, which is what? Say if I have 1,000 people, 1,000 rows with me, one single column of their height values. What we need to do is we need to multiply it with the weight matrix. A weight matrix should look something like this. The weight matrix should be 1 into 1,000. So you'll have weight 1, weight 2, weight 3 goes on up to weight 1,000. For every data point, right, he will get his own weightage. So you're saying this is going to be the weightage matrix. Now when you multiply, what will happen? The number of columns in the first matrix is equal to the number of rows in the second matrix, right? So A into B, A cross B, when you're multiplying with B cross C, these two people should match. The resultant output will be A into C. So the output here will be what? It will be 1 into 1. So the output here will basically be 1 into 1. Then you add it with the bias, who is also a simple scalar here. Then you will finally get a single value as a prediction right now. Right? So what are we doing right now? We're basically saying, hey, these are the weight values, these are the input values. We'll multiply it with these members, add it with their weights, then you'll get the final result is what we are saying. Okay, so actually I think I'm making a small mistake. So weight transpose, I shouldn't be getting a single prediction. I should be getting a vector of predictions, because a lot of weight values, a lot of things. W transpose X plus B 1 into 1,000, or it should be X transpose W plus B. Correct. It should be X transpose W plus B. Ideally, you should get what? Just give me a second, guys. So we have a column full of data. So the column full of data will be 1,000, 1. The weight vectors will be this one, 1 into 1,000. When I multiply, it will be 1 into 1 plus the bias, 1. But that's not how it works. I should be getting once again 1 into 1,000. One column for all 1,000 people. Anyways, so don't worry about this one. I'll just come back on this one here. You're doing some small mistake somewhere here. Okay. So don't worry about this one. So what actually we are trying to understand is, you can see here, guys, he's taking a single column of data, right? He's going to multiply it with the weight matrix. The output will also be a single column of data. That is, you gave a height column. He will give you a predicted weight column. So that's why he's saying it's a single column, but with a lot of data points for a lot of people is what he's saying. So okay, so if it is 1 into 1000 into 1000 into, it shouldn't become 1000 into 1000. So 1 into 1. I don't know, somewhere we're missing it. I'll just come back on this one. Okay. So you can see here. So what we're actually doing is we are saying, hey, it's a single column of data. You're going to initialize some weight values and all on the inside. I'll talk about the weight values and all more coming. So it's going to be completely random. Then he will just do input into weights added with the bias. He'll give you a single column output. So I gave you a single input column, which is, let's say, height. You give me a single predicted column, which is weight. How many parameters is he estimating? 2 parameters. Why? There is a weight parameter, there is a bias parameter. So how many parameters is he supposed to estimate? 2 parameters. One is weight, one is bias. So it's a dense layer you have added. The output is going to be a single column of data. There are 2 parameters I'm estimating. One parameter is the weight, another parameter is the bias. Now see here guys, we haven't compiled it. Now when I go back and ask him to create the model, it will give us an error saying the model needs to be compiled because he first has to convert it as a TensorFlow graph and all. That's why we are compiling it. Now let's go back and hit Control Enter. The model will start training. So what actually he's doing is, he's going back here. You have the inputs. He has assumed some weight values, some bias values. That is some set of coefficients. And he's giving you an output. So he's saying, this weight and bias that I've assumed, I'm calculating what is the output. Based on that, I will know what is the error. Now using the error, I will go back and change my weight and biases. So it is called as a back propagation. Then I will predict again. Okay, so I'm predicting once, I'm finding what is the error, I'm rectifying the weights and biases to reduce this particular error. This is one single epoch. So what is a single epoch, guys? I pass an input with the weight and bias, you give me an output. Based on the output, I calculate the error. This error I will just rectify using a back propagate. This becomes one epoch. Then I'm saying, okay, with the new weights, let's go back and compute the output. I see the error. Now we'll once again come up with a new weight here. So using this new weight, let's go back and compute the output. You will get an error. You're updating the old weight with once again a new weight. So this cycle keeps happening again and again and again. You can decide how many cycles to keep. For now, you can see I have kept 50 cycles where he's saying, hey, I assumed some weight and bias values. Okay, I got an error of 55,000. Next, I'm trying to rectify it. I came up with a new set of weight and bias. Now my error is reduced to 46,232. Then next time I'm trying to improvise it, it became 38,000. Then I'm improvising to 31,000. Then it became 25,000. I'll keep trying to improvise it first, further going further and again. You get somewhere around 565 as an error after 50 iterations here. So we are doing this epoch what? How many times? 50 times. I predict, compute the error, I rectify it. I predict, compute the error, I rectify it. It keeps happening again and again and again for 50 different epochs. At the end of 50 epochs, you can see the error is reduced to 565 units here. What shall we do right now? We can just go back and fetch what are the parameters of this particular predictive model. So you can see here, we have this function, okay? Something called get weights. So let's hit Control Enter. Let's just come down. The W that he has come up with is basically 2.42 and the bias that he has come up with is basically 1.82. I don't think it is anywhere nearing to our original solution. I'll tell you why. So let's just come down here and we'll create a quick scatter plot of it. You can see it is not yet a perfect model. So it's not a perfect linear regression yet, right? So the previous linear regression that you created was looking like this. So the linear regression that we have created now is not still perfect. What do we need to do? We need to increase the epochs. So I'll make it probably as 150. Okay. So we are saying model sequential, add it, compile it, summary. We'll ask him to start creating it. So 150 times, He's predicting, he's rectifying, he's predicting, he's rectifying. It keeps happening for 150 times, which is the 150 epochs that we're talking about. Let's see how much the error is getting reduced. It has become 547 and all. Now let's get the weights and biases. Still not perfectly close to that guy. Why? Because let's go back and visualize it. Visualize it. This is the reason. Okay. So I'll actually use this particular configuration. Okay. I'll not deep dive into the configuration for now. It's a little too higher for now. So let's keep it like this. So sequential, dense, summary, epochs, batch size of 1000. Okay, so let me probably make it as 500. Okay, 570, 568, 565, 564. It's not yet perfect. Okay. So what did we get here as weights? I mean the coefficients. We got 7.71 and minus 350. But what we're getting here is a little different. Why? Because once again the same reason. Our linear regression model is something like this. Okay. So what I'm doing is, guys, using the same X, I'm kind of predicting. Okay. Then we are just trying to take up the true value and the predicted, and we are plotting it. It's still not a perfect linear regression model. So I need to go back and run it. Probably another 500 times I'll run it. Let's see what happens. Okay. Now let's see. I don't think there should be much of a change. Anyways. Okay. So I think we are missing out somewhere on the optimizer or something. Anyways, not to worry much about it. Okay. So this is exactly how we can create a quick linear regression model using neural networks. Okay, so what we have basically done is we have created a single perceptron here. That's all. So, you're basically going and saying, hey, let's import the sequential model API. Let's import a dense layer. That's why you keep adding your perceptrons. So we are saying model is equal to sequential, model.add of dense layer. We're saying it's a single perceptron. So input shape is 1 comma blank, which means one column I'll give you, and I will give you what? Lot of data points, right? So what we're doing is we are saying activation function is linear, by the way. Here on the input, you can also say activation function. So we're keeping it as linear, which means identity, give me as it is. Then we are monitoring mean squared error. We are asking for the summary. Okay. So you say it's a single layer I've added. The output shape is going to be one column of data, but for a lot of data points. And you can see number of parameters I'm going to estimate is 2 parameters, a weight and then a bias here. So these are the 2 parameters that he's going to probably use. Then we went and said, hey, can you do the epochs 500 times? I'll tell you what a batch size is. An epoch is basically what? Going back and predicting, then reconciling and going back and rectifying it again. That is what is called as an epoch. We are probably doing it for 500 times here. Okay, so let me give it one last try. Keeping it 512 also doesn't seem to help us much. Okay. After 568 or something, it's just taking a small thing. Okay. Okay. So this is exactly how we imitate a linear regression model using perceptron. That's not the idea here. The objective is to help you all understand that a single perceptron is nothing but, actually speaking, a linear regression model. So that's exactly what you need to understand, right? Getting it, guys? Are you all with me till here? Are you all able to follow this entire concept of what is multi-layer perceptron? What is this single perceptron that we are talking about? What is this input into weights plus bias? How is it equal to a linear regression model? How do you write the Python code of it? Are you all with me till here? Yeah? Okay. Okay. So now let me ask you all a quick question. So the same perceptron, right, which was helpful for us in creating a linear regression model, how do you think you can probably make him imitate how a logistic regression model might work? Can you all tell me? How do you think that's probably possible? So the question is, the single perceptron was used in the creation of a linear regression model. How do I probably use the same guy to probably imitate a logistic regression model? Any thoughts on how we can do it? Yes. So what is probably the change that you need to do to make the perceptron function like a logistic regression model? Normalize? No. Add a function to it? Okay. What function, Anu? I perfectly agree. You have to add a function to make it non-linear. But still, saying that it's going to become nonlinear is not right, because logistic regression model is still a linear model. Only towards the end you're kind of making it to take a small cutoff, a shape kind of a curve. You're perfectly on the right lines, but just tell me, what function do you probably add? So tell me, guys, the equation difference between a linear and a logistic regression. Can you all tell me what is the equation difference? Here, linear regression was y is equal to beta naught plus beta 1 times of x. In logistic regression, it was what? Can you all tell me? So in logistic regression, it was what? Ln of p divided by 1 minus p is equal to beta naught plus beta 1 times of x, correct? But we didn't want this equation. So we said, hey, I'm going to still create a linear regression model, or my perceptron is still going to predict what? Beta naught plus beta 1 times of x. But the logistic regression is going to give me an output, right? So how do you guys think we can make this beta naught beta 1 times of x to become an output that logistic regression needs? What is the formula? What is the equation? What happened, guys? The output is basically probability. What is the equation for probability in a logistic regression model? It is exponential of beta naught plus beta 1 times of x divided by 1 plus exponential of beta naught plus beta 1 times of x, isn't it? Thanks, Manohar. Yes. So it is exponential of beta naught plus beta 1 times of x divided by 1 plus exponential of the same. What is this function? Do you all remember I gave you a name, something called sigmoid? So all you need to do is to the perceptron, who's going to give you beta naught plus beta 1 times of x as an output, ask him to convert it as exponential of beta naught beta 1 times of x divided by 1 plus exponential. How can you do it? You can ask him to an apply function, something called a sigmoid. That's all the work is done. So you're basically asking him to take up that particular beta naught plus beta 1 times of x, which the perceptron will give you, and convert it as sigmoid of that beta naught plus beta 1 times of x, which is equal to the logistic regression model that we wanted. So let's go back to the logistic regression case. So I think this is also something that we did discuss, isn't it? So we have this, user, how much time are they probably spending in a particular store? We need to find whether spending the time is kind of dependent on buying a product or not, or opposite. People buying a product or not, is it dependent upon the time that they're spending? Right? So the predictor is basically time, the target is basically buy. 1 means yes, the customer did buy, 0 means no, the customer did not buy. So this is how the plot looks like, correct? We created a logistic regression model, and we can see that, we got the coefficients, right? Which is model dot coefficients, right? It was 1.53 and model dot intercept should do it. It was minus 2.65. So this was basically the logistic regression model that we came up with, beta naught and beta 1, isn't it? Now what we're going to do is we're going to make the perceptron to do the same job. We'll say from keras.models import sequential, from keras.layers import dense, keras.optimizers import atom. We are saying sequential model API. Let's add a single layer. So how do we define it as single layer? If I keep it many number of times, it will become these many layers. First layer, second layer, third layer, fourth layer. So there are 4 layers. But since I'm copy pasting this piece only one time, it's a single layer. In the single layer, we have a single perceptron who will receive a single column. and the output he will compute will be passed on to a sigmoid function as an activation. Control enter, model.summary. So you can see we have a single layer. He's going to give you one single output. There are two parameters he's estimating, which are weights and biases. Now let's go back and say, hey, give me the Adam optimizer. The loss is something called binary cross entropy, which is otherwise the MLE equation that we spoke about, or the log loss that all of us know. MLE equation is what? Yi times log of probability plus 1 minus yi times log of 1 minus probability, isn't it? This is MLE equation or the log loss equation. The other name for it in deep learning is called binary cross entropy. So hitting control enter, it's binary cross entropy. Let's go back and create the model. So you can see log loss was pretty high, 0.86. It came down to 0.85, coming down to 0.76, 73, 72, 69, 59, 55, 54, 53, and it came down to 0.4905. So this is exactly how you create a logistic regression model using this perceptron. Now we will go back and say model.get underscore weights. Control enter. So he's saying the weights are 0.81 and minus 1.15. But what did we have here? We had a little different. 1.5 and minus 2.65. Once again, the same problem. I need to go back and run it for many number of epochs. Then it will be closer. So if I probably run it for another 500 epochs, it will be much more closer. Okay. So the scikit-learn is having a beautiful methodology to solve it. That's why it's giving you a perfect solution. This guy, he'll get more and more perfect if you run it. Now can you see? It became 1.15 and minus 1.91. We wanted something very similar to that, right? So you can go back and run it another 500 iterations. Okay, now you can check the weights again. Now it has become pretty close. 1.46, which is pretty close to the 1.53 that we are talking about. And we got minus 2.47, which is pretty much close to the minus 2.68. Right? So this is exactly how you create a logistic regression model using a perceptron here in neural networks. So we're using a single perceptron and we've imitated both what? A linear regression model as well as a logistic regression model here. Now go back and predict it. You can see it's a beautiful S-shaped curve, something like this. So there's a prediction we are coming up with. These are the predictors we have. So you can see this is the model's prediction, a beautiful S-shaped curve like this. Now I think everybody should agree why we keep saying it's a S-shaped curve, right? So this is the prediction he's coming up with. Now if I keep a 50% threshold, saying if the probabilities are above 50, keep it as 1, else keep it as 0. This is how the thing will look like. So he's saying anybody who's spending more than 1.5 minutes, they are more likely to buy. People are spending less than 1.5 minutes, they are not likely to buy. So this is basically the prediction that we're coming up with here. Now you can go back and ask for what is the accuracy scores and all we have got. Okay, so the accuracy. So the accuracy has been 83%. So it looks cool. So the Keras model that we created, which is an equivalent of the logistic regression model, is able to give us 83% right now. So it looks good, right? Yes. Do you all agree with me, guys, on why do you think, adding a sigmoid here at the very front is making the perceptron to behave like a logistic regression model? Are you all convinced with this one? Yes. Any questions on this perceptron thing? A single perceptron in a multi-layer perceptron model. How is it functioning? Any questions? It's basically equal to a linear or a logistic regression model. That's all. So to make it more and more better, you can play with the activation functions. We have different activation functions to discuss. Tell me, guys, any questions till here? I'll wait for a minute. Okay, that's a good question. Why is it called as deep learning? Very nice question. So the answer to the question is in the next discussion that we're going to do, which is basically multi-layer perceptron. So we just discussed about what is a perceptron, correct? Now is we are saying, hey, it'll become a multi-layer perceptron, which means I can create my level one, sorry, a layer one. So we are saying, hey, this is going to be my layer one. In this layer itself, I can probably add 3 predictive models, 3 perceptron. That is what I'm saying, 3 predictive models. So there is an input, okay, that is height of a person. I'm giving it to the first perceptron, second perceptron, third perceptron. He will have weight 1, he will have weight 2, he will have weight 3. So what will happen is, generally to the entire layer itself, there will be a single bias. So he will have a single bias. The same value of bias will be with this guy, the same value. But you can of course pass separate biases also, it's okay guys. But in Keras, the way they have designed it, for the entire layer, it will be a single bias. So the same bias value will be shared by all the people. So he will calculate y1, he will calculate y2, he will calculate y3. Now what we will do is we'll say, hey, I will add a second layer, okay? The second layer will probably have 5 predictive models right now. So we're saying, let us have 5 predictive models in this case. Okay, so what will happen is model 1, perceptron 2, perceptron 3, perceptron 4, model 5. So I have 5 models right now. This will become my layer 2. Now what he is doing is he is saying, hey, I have computed something, boss. I will share it with all of you. He is saying, hey, I will share my results with all of you people. Then this guy says, hey, I have computed something. I will also share my results with all of you. Then the last guy is saying, hey, I have also computed something. I will share my results with all the 5 of you. Basically, guys, you can see that in layer 1, there are 3 predictive models, model 1, model 2, and model 3. So what is happening? 3 models are giving us a prediction. You could have just done what? Done P1 plus P2 plus P3 by 3. That could have become your final prediction. That is good enough. But what are you doing? You are still saying, I'll have another set of models. So I'll call this as M4, M5, M6, M7, and M8. The role of a M4 is he will get the output coming from M1, M2, M3, and he will tell me, okay, let us not do a plain average. I have understood that you can give 70% weightage to M1, 10% weightage to M2, plus 20% weightage to M3. That is what this guy is telling. Well, this guy is telling us, hey, I have a little bit different opinion, okay? I will give 60 to M1 and I will give 20 to M2 and 20 to M3. Similarly, every model here that you see, they will share their opinion. The simplest thing that you could have done is create the 3 predictive models and do a plain average. But what are you doing? You're saying there are 5 other people who will decide it. So let's say you are a team, okay? You're doing a project. There are 3 people in your team. All the 3 of you are going back and doing some research for a particular objective. Now, what are you doing? You're not sharing your results with yourself saying, hey, let us all take up our results and do an average. You're not doing that. You are giving it to a panel of 5 people. So there is a jury, there is 5 people. So the first professor is saying, hey, I'll give 70 marks to what M1 is telling, 10 marks to M2 and 20 marks to M3. But the second judge or the second professor is saying, I'll give 60, 20, 20. In the same fashion, all the 5 people will share their opinion. You still have 5 answers. All you need is one single answer. Then what will happen? The HOD will probably come and he'll say, okay, all of you share your results with me. I will do a plain average right now. So it is not the 3% average. You're taking an opinion of another 5 people, then you're averaging those 5 people's opinion. So you're trying to make the model better and better. You're saying, let us not rely on only the 3 of your results. I'm going to rely on another 5 people who may enhance the output coming from the previous stage. I can add another layer. He will enhance the output coming from the previous stage. So every layer you keep adding, guys, is an enhancement of the output coming from the previous stage. So layer 2 is saying, I will enhance the output coming from layer 1. Layer 3 will say, I will enhance the output coming from layer 2. Every layer you add is actually enhancing the output coming from their previous stages here. That is exactly how you go back and create a final model here. So you're saying it's a multi-layer perceptron. Within one layer itself, I can have multiple perceptrons, and I can keep adding multiple layers also here. Right? So now you're adding 2 layers. You can go back and add a 3rd layer also if you want. Right? So I'll add a 3rd layer. Okay, so we are adding a 3rd layer of perceptrons here. We're going to go back and add a 4th layer of perceptrons right now. So we'll say, hey, I need a 4th layer also right now. Then I will probably go back and average it. Here you may probably have 6 predictive models. Here you can have probably 3 predictive models, and you'll finally average it out. So this is exactly what is called as a multi-layer perceptron. So every layer is trying to enhance the output coming from the previous case. Example, let us take up an image, okay? So when you pass an image, the first 3 people, right, what they will do is, they will help you understand the edges available in the image. The second guy will enhance it a little bit more. The third guy will help you find the patterns. He will help you find more. The fourth guy will go deep dive and he'll research much more. So what should happen is, it's like every layer that you see is going to enhance the output coming from the previous layers. Okay, so actually speaking, how it should be like, in the first layer only you should have maximum perceptron. Then it should keep reducing. I've done the opposite here. It's actually completely wrong. I shouldn't have done like that. I'm sorry. So in the first layer is where you'll have more number of people. Next set of layers will be less number of people. So typically in the first layer, if you should have created 8 models, here 6, here 4, then 3. It should always keep decreasing. I'll tell you why it should be decreasing. Okay, I'll probably tell you in the next class tomorrow. Basically, it's all mathematics. There's a reason why we keep decreasing. So it should keep decreasing. The output coming from 8 people is validated by 6, validated by 4, validated by 3, then finally one single output you will have. So you keep adding lot of layers, guys, and within every layer you are adding different predictive models. Now just imagine, till now a single linear regression itself we were happy, a single logistic regression itself we were happy. Now see, 3 linear or 3 logistic, 5 linear, 6 linear, combining so many models together, you have total like 15 to 20 models. 1 linear regression versus 20 linear regression. Who is the clear winner? This guy here. 1 linear regression versus a 20 linear regression models. The clear winner is a artificial neural network or a multi-layer perceptron that we are creating here. He is the guy who's going to combine the predictive powers of a lot of people. Right? He's coming together with the combined predictive powers of a lot of people here. Now, if you all ask me the question, why do we call it as deep learning? The answer is certain complex data sets like images, right? So when you give the face of a person, complex data sets like images, you can't achieve it using 3 or 4 layers. It's typically constructed for many layers. So layer 1 will be pretty massive. Layer 2 will be a little lesser. There will be a layer 3. Okay, layer 2, you'll have layer 3, you'll have layer 4, you'll have layer 5, layer 6, layer 8. It'll keep going on and on and on. So first guy will capture maximum information, second guy will enhance it, third guy will enhance it more, fourth guy will enhance it more. It keeps happening in a what? Forward fashion here. Everybody is trying to enhance the output coming from the previous stage. So more the number of layers, more is the pattern you will learn. At the same time, more is the noise also you will learn. So always more is not the best. Sometimes you need to keep it lesser also. Okay. So more the number of layers, the more better off we are. Why did we call it as deep learning? Simple. Artificial neural networks have been existent since your 1990s and 80s, or even since 70s, I think. But it has been implemented from 90s onwards. Since you had decent computers, people were creating 3-layer models. The Mario game and all we see, right? It's actually a 3-layer model only. But today, the Google Translate that you see, or the Google's image search you see, or the Google's own voice capabilities that you see, they're all deep learning models, because 3 layers alone will not help us analyze complex data like voice or images or something. You need pretty massive number of layers here. And that was pretty much possible after the invent of GPUs, graphical processing units. Till date, we have been using CPUs. Today, we have GPU systems, graphical processing units. So CPUs are capable of doing variety of tasks at a faster time. But if you give a single task, he will do it very slowly. But GPU, if you give him a single task, he can do it at a lesser amount of time. But if you give him many tasks, he will basically start failing. So that is more like a trade-off. CPU is handling many tasks at lesser time, but single task will take more amount of time. Here, many tasks will take lesser time, but a single task will take, many tasks will take more time, single task will take up lesser time. So that's why GPUs are very, very preferable for doing things like image processing. Since the invent of GPUs, right, you were able to create very deep models and all. CPUs were not able to handle anything more than 5 or 6 layers or complex big data sets that you see today. Today, big data sets like images are all what? GBs. We get data sets in images, in GBs. To solve all those, you need some good computing power. Only when the invent of GPUs, it was possible. And GPUs came like what? Just 5 years or 10 years back. It was just a decade back that these things came into existence. That is when people started calling this as deep learning. So artificial neural network is a name that was given, let's say, in your 20th century, but deep learning is something that is given in this 21st century. That's all. It is just a different name. The limitation which was seen in the 20th century is no more a limitation here in the 21st century. That's it. Okay. You're having better computing powers today. You're able to create pretty deep models here with many layers. That's why we have a separate name itself for today's neural network models that you're creating, something called as deep learning models. Okay. But otherwise, they're all the same, guys. Artificial neural networks, deep learning, right? Artificial intelligence, it's all the same. Okay, they're all pretty much the same. So when you come into the specific model types, we have things like multi-layer perceptron, we have convolutional neural networks, we have recurrent neural networks, and many other about to follow. Okay. Yes. Tell me, guys, are you all comfortable with all these things that you've discussed till now? Are you all convinced with all these things that we've discussed till now? Perceptron, how do you create a perceptron? Why do we call this as multi-layer perceptron? Why do you think is a multi-layer perceptron going to do better over single perceptrons? Does everybody agree? Okay. Okay. Perfect. So I think with this, probably we can call it a day. Okay. So let's probably call it a day, guys. So what we'll do tomorrow is we'll start off with this one. We'll discuss more about the maths behind solving a multi-layer perceptron. So how do we solve it? Then we'll jump into optimizers like gradient descent, stochastic gradient descent, Adam, Adabos, not Adabos, other things. Uh, what is that? RMS propagation, things of that sort. So those are the different topics that we're going to be discussing. And we'll see the use case also that we spoke about, the home lending credit use case. Okay, great. So if there's no questions, I think we can probably call it a day. Yeah, shall we? So there are a lot of questions. Any reading material for neural network? Okay. Any reading material? I think I have one PDF with me, which I can share it. I'll upload it. Okay. Oh, it was interesting. Thanks, Anu. Great. Okay, so let's call it a day then. Yeah. Thank you guys. Thanks for joining. We'll catch up tomorrow at the same time.